Imagine a notebook where you write down every change you make to a puzzle before you actually move a piece. If the table falls and the puzzle is knocked over, you can look at the notebook and rebuild the exact picture that was there before the accident. In a database, the notebook is called a log. Log-based recovery is needed because computers can lose power, crash, or have disk problems, and we must be able to bring the data back to a correct state. Without the log, the system would not know which changes were finished and which were only half done, and the database could become corrupted. The log gives us a reliable way to undo bad work and redo good work after a failure. The log is like a diary with many entries. Each entry is a log record that tells what the transaction did. For example, add $50 to account A. Every record gets a unique number called a log sequence number, abbreviated LSN, similar to page numbers in a book, so we always know the order. There are three main kinds of records: redo records that tell us how to repeat a change, undo records that tell us how to reverse a change, and compensation log records, known as CLRS, which are special undo records that say I already undid this step. A transaction's actions are written as a sequence of these records, each with its own LSN, so the system can later walk forward, redo, or backward, undo safely. Write-ahead logging, abbreviated as WAL, is a rule that says write the diary entry to the log before you change the puzzle pieces on the table. In computer terms, the database must flush a log record to stable storage disk before it writes the corresponding data page to memory. This guarantees durability. Once a transaction reports that it is committed, its log entry is safely stored, so even if the power goes out, we can later redo the work from the log and the transaction will never be lost. WAL separates the fast, volatile memory where data lives from the slower, safe place where the log lives, ensuring the log is always ahead of the data. A checkpoint is like taking a photo of the whole puzzle at a certain moment. The system writes a special checkpoint record to the log that says all changes up to LSNX are already written to the database files. After a checkpoint, old log records before X are no longer needed and can be truncated, deleted to save space. By checkpointing regularly, we make the recovery window the amount of log we must read after a crash small. Because we only need to redo actions after the last checkpoint and undo any unfinished transactions that were active at that time. A RIES, algorithm for recovery and isolation exploiting semantics, works in 3 steps. Analysis: scan the log forward from the last checkpoint, build a table of which transactions are still active, and note the highest LSN of each page. This tells us where to start redo and which transactions need undo. Redo, starting at the smallest recovery LSN found in analysis, replay every redo record in order, applying changes to the database pages even if they were already on disk. This makes sure all effects of committed transactions are present. Undo, walk backward through the log, using the list of unfinished transactions from analysis. For each undo record, apply the opposite change and write a CLR to the log. This removes the effects of transactions that never committed. The 3 phases guarantee the database ends in a consistent state. The process is like reading a diary from the checkpoint day to the end, first copying every event forward, redo, and then erasing the unfinished stories by walking backward, undo. Different failures need different actions. System crash, power loss, OS crash. The memory is gone but the log on disk is safe. A RIES analysis: redo and undo restore the database using the log. Media failure: disk platter crashes. Part of the log or data files may be missing. Replicated logs or backup copies are used after restoring the missing pieces. A RIES is run. Logical errors: buggy application that writes wrong data. The log still records what was done, so an administrator can manually undo the bad transaction by issuing a compensating transaction, or by using the log to roll back to a point before the error. In all cases, the log is the source of truth that lets us reconstruct what really happened. A LSN is a numeric stamp that increases with every new log record. LSN 0 equals 0, start of log. LSN I equals LSN of I minus 1 plus size underscore I. Size underscore I equals bytes of the ITH record. If record 1 is 100 bytes, record 2 is 80 bytes, and record 3 is 120 bytes, then LSN1 equals 0 plus 100 equals 100. LSN2 equals 100 plus 80 equals 180. LSN3 equals 180 plus 120 equals 300. Because LSNS are monotonic, always increase, comparing two LSNS tells us which happened later. LSN3 greater than LSN2, so record 3 happened after record 2. When a page is written to disk, we store the page LSN, the LSN of the last change applied to that page. During redo, we only apply a record if it's LSN greater than page LSN, meaning the change is newer than what the page already contains. This simple math lets the recovery algorithm quickly decide what to redo or skip. To make logging fast, systems use several tricks. Group commit instead of flushing each transaction's log record individually. The system batches several commits together and writes one larger block to disk. It's like waiting for a few friends to finish writing their diary entries before you all hand the book to the librarian at once. Log compression, redundant information, e.g. repeating the same column name, is encoded more compactly, reducing the amount of data written and read during recovery. Parallel redo, undo. Modern databases split the log into independent sections by transaction or by page range, and let multiple CPU cores apply redo or undo work at the same time, similar to several workers, fixing different parts of a broken puzzle simultaneously. These optimizations keep the overhead of logging low, while still preserving the strong safety guarantees of ARES.